Hello and welcome to 3.1 Types of Forces. This is the start of Unit 2, all about forces. In Unit 1 we learned about kinematics, which was how things move. In this unit we're going to be learning about why things move. And that's called dynamics. Dynamics is the study of the causes of motion. The causes of motion. And of course our unit is called forces. The most important thing here is a force. A force is any push or pull. Anything that pushes something or pulls something, that's called a force. Our units are called newtons. This is the unit for force. And the conversion here is that 1 newton is equal to 1 kilogram times meters per second squared. 1 kilogram meter per second squared. And we're going to see where that unit comes from soon. To measure forces, we can use devices called spring scales or force sensors. And basically a spring scale is the more old-fashioned way of measuring something. It's the analog way. The idea is that we actually have a device that has a spring in it, and when you pull it, it measures how far it's been pulled, and that tells you how much force has been applied. A force sensor would be an electronic device that does the same thing. It tells you how much force is being applied. Okay, now we have two really important ways that we need to draw our problems here. It's really important, really important when we're dealing with forces that we draw our problems so that we can understand exactly what's going on. There's two ways of drawing our problems. That's system diagrams and free body diagrams. A system diagram is a simple sketch of all objects in a situation. And we're going to do some examples down below. So a system diagram is just a sketch of the situation. Whereas a free body diagram, this is the one we're going to be using a lot in this unit. This is again a simple drawing. But this one is just of one object. Showing all forces acting on the object. All forces on it. So we've got our examples down below. This first one here, this is a system diagram. And you can see that's a sketch of the situation. There's a hand holding a book. Now that's a pretty good sketch. If you were to make a system diagram, it probably wouldn't be this detailed. And this one here, this is a free body diagram. And look at that difference here. The free body diagram, it's just a box with some lines coming out of it. That's what every free body diagram is going to look like. It's a box with some lines coming out of it. Each one of those lines is a force. So each one of those lines is either a push or a pull on that object. This is actually the free body diagram of that book there. The book has gravity pulling it downwards, and it has an applied force pushing it upwards. That's from our hand. Okay, let's get some terms here, because I just talked about these different forces. We've got a whole list of different forces down here, so we're gonna go through this list. First off, applied force. We call this FA, and each one of these forces is going to have a different name with a letter. So FA is for the applied force. This is a force caused by an object pushing or pulling. If we have some object that's pushing or pulling something else, That's giving it an applied force. That's a pretty broad category, and you're going to see the rest of these have more specific scenarios. So tension, Ft. Notice there's an arrow over it. These are all vectors. Tension is when a rope or string is pulling an object. And notice it's only pulling. Tension can only pull. It can't pull. It can't push, sorry. And hopefully that makes sense. If you have something tied to a rope, you can't push the rope to push the object. The rope just sort of curls up. Okay, our next one here is the normal force. We're going to be seeing a lot of this force here. The normal force, Fn, is when a surface pushes back on an object. So for instance, right now you're probably sitting in a chair or standing somewhere. Gravity is pulling you downwards, and that's soon on our list. Gravity is pulling you downwards, and the floor, or your chair, is pushing you back upwards so that you don't fall down. That's called the normal force. That surface, your chair or the floor, is keeping you from falling downwards. It's pushing you back upwards. So that's a normal force. And the other thing we can say here is that Fn, the normal force, is always perpendicular to the surface. Whatever surface is giving us this applied force, Fn is always perpendicular to that surface. Good. Two more forces on this list here. We have Ff. This is for friction. Friction slows things down. Friction always tries to stop motion. And it acts in the opposite direction of the motion. So if I'm moving forwards, there's going to be some friction that's slowing me down, some friction that's forcing me backwards to slow me down. And we're going to be learning all about all of these different forces. Right now we're just getting a quick overview. Our last one here, gravity. You're probably familiar with gravity. This is the force of attraction Well, I'm going to stop for a second here. Gravity is the thing that pulls you towards the Earth, right? It's what makes us heavy. It's what makes us not float away from the Earth. But it's not just the Earth. There is gravity between everything. Any two objects have gravity between them. And the only reason why, for us, we only care about the Earth's gravity is because the Earth is so much bigger than anything else we deal with. And it's also closer. The sun is even bigger than the Earth, but it's further away. So we just feel the gravity of Earth. But if you've got a pen in your hand, you are experiencing gravity from that pen. You're experiencing gravity from the table. Everything pulls itself to other things. So this is the force of attraction between any two objects. Now in this course we focus on Earth's gravity. So we actually have an equation here for gravity. The force due to gravity is equal to mg. And we've dealt with g already, where g is 9.8 meters per second squared. And there we go. I'm actually just going to turn that into a vector. I'm going to say that this is 9.8 meters per second squared down, always pulling us towards the Earth. So in this course, we're just dealing with gravity from the Earth. Okay, we've got a picture down here. So I want to do a diagram where we're looking at all the forces on this picture here. First off, this is a sketch of the situation. This is a system diagram. Good. We're going to draw a free body diagram. We always start with a box. No artistic talent needed for this. We just start with a box, and we draw all the forces on this. Usually we can start with gravity. Gravity is usually easy because it's always going downwards towards the center of the Earth. Okay, let's look back at this picture here. We've got gravity pulling us down. The ground is pushing us back up, so we're going to have a normal force upwards. I can put that over here. Here's our normal force. Okay, and then we have this girl over here is pushing the object. If that girl is pushing it, she's directly pushing it, she's giving it an applied force. Notice that even though she's on the left, she's pushing it this way, she's pushing it to the right, so we draw the force coming out the right side of our box. Okay, and then we have another force here. The boy is pulling on this rope. Remember, rope is special, so if we're dealing with rope, that means we have a tension force. Again, it's coming off in this direction, Ft. And we're almost done. But remember, if something's moving, then there's probably friction slowing it down. So we've got our tension going this way, we've got our applied force. Friction's going to be slowing it down back in this direction. F, F. And there's our free body diagram. That's how we make free body diagrams. Okay, let's pop on to the next page here. We've got a bunch of situations, and we're going to draw the system diagram and the free body diagram for each object. Remember, FBD, that stands for free body diagram. Every single problem that you do in this unit should have a free body diagram. Here's our system. We have a cup sitting at rest on a table. Okay, so I'm going to draw a little table here. Again, I am not an artist. So, something like this. Here's the legs of the table. Cool, that looks like a table. And now we'll draw a free body diagram. Remember, the system diagram, we just draw the whole thing, just a little sketch of what's going on. We have a cup on the table. But we want to draw the free body diagram just for the one object, the cup. And FBD is always just one object. Here's our cup. It has gravity pulling it down. And it has normal force pushing it back up so that it doesn't fall downwards. That's it. Next one. A large trunk in the basement is pulled by a rope tied to the right side of the trunk by a person. The trunk does not move. A trunk, it's like a big wooden chest or a box. So we're going to draw this big wooden box, something like this. Okay, and we've got a rope tied to it. It's being pulled in this direction by some person here. Here's our person. We're pulling it, but the trunk doesn't move. So we're trying to pull, the trunk isn't actually moving. That's our system. And here's our FBD. Let's see. Gravity. Always a good one to start with. Normal force. Friction. Friction is keeping it from moving. And we've got our applied force, or in this case actually it's a tension force because we're pulling a rope, Ft. Now notice I've drawn that tension force up on an angle because probably, if you look at our picture, probably we're pulling it up on a bit of an angle from wherever it was tied. Maybe not, maybe it's a different situation, but that's just my feeling about this. Alright. Now we're going to be learning, by the way, how to use these diagrams, use these free body diagrams to solve the problem, to figure out what all the different forces are, but that's beyond us right now. We're just learning how to draw them. Next one, we have a baseball player sliding to the left across the ground. Okay, here's our system. Alright, this is where we need to get a bit artistic here. We've got a plate maybe that the baseball player is sliding towards. And we're going to have this baseball player sort of sliding off like this trying to catch that base before they're tagged out. Something like this. And they're sliding in this direction. Perfect. Here's our FBD of that situation. We want to draw the person. Here's our person. Gravity. Normal force. And our last one here, well, maybe there's more than one, but I guess I've spoiled it already. We only have one more force. This person is sliding this way. As they go, they're slowing down, right? They're going to stop at some point. All they have acting on them here is friction. Friction is slowing them down, and there's no force pushing them forwards. Remember, if there was going to be a force over here, something would have to be giving it that force. We don't have anything to give it a force forwards. So that's our free body diagram of that picture. Last one. A desk is pushed to the left across the floor. We're going to draw our desk here. Something like this. And we got some person here pushing it to the left. Goes this way. It's usually a good idea on your system diagram to draw some sort of direction of motion. And an FBD of our desk. Again, we have gravity, normal force. We're pushing it to the left so it has an applied force. We sometimes call this an action force as well. And again, we usually have friction. So friction is going to be slowing it down a bit. Okay, there we go. There's some diagrams. Now this is, as you've probably noticed, a long lesson. So we've still got a bit to go. Number 3, we want to calculate the net force. Net force, we call this F net like this. So we can add this to our list of different forces. But net force is a bit special. Net force is the total force. And the way that works is it's the sum of all forces acting on an object. So we need to add them all together. Now they're going to be in different directions. So we're probably going to have to do some 2D vector addition sometimes when we're doing these sorts of problems. But that's what our net force is, and it's a very important concept. When we take all the different forces acting on something, we add them all up. Well, if we have a force to the left and a force to the right, if they're the same, then that adds to 0. If we have a force up and a force down and they're the same, that adds to 0. But it could be unbalanced, and we could have maybe the left force is larger than the right. That means that our net force would be something like this. Or if the left one and the up one were larger, then we could have a net force on some angle here. It's really, there's a lot of different scenarios here, and we're going to be learning in the next lessons why the net force is important. For now, we're just going to learn how to calculate it. Here it says that the floor exerts a normal force of 36 newtons up on a stationary chair. The force of gravity on the chair is 36 newtons down. Draw the free body diagram of the chair and use that to determine the net force on the chair. Okay. Every single force problem should start with a free body diagram. Gravity, normal force. I can't tell you how important it is to draw one of these pictures. It always helps you solve it. In this case, our net force, here we can see we have Fn upwards, Fg downwards. So I want to add them together. They're in opposite directions, so I can do this by saying it's going to be Fn. Well, let's add them as vectors here. Let's do some proper vector addition here. Fn plus Fg. This is what we're dealing with here. So Fn is 36 newtons up, and Fg is 36 newtons down. Now, If you remember from Unit 1, up and down, those are opposite directions. So to add these together, I need to flip the second one. I can say this is minus 36 newtons up. 36 down becomes negative 36 up. And now we can do this here. We have 36 minus 36. That gives us a grand total of 0 newtons. And 0 doesn't have a direction. 0 is just 0. We also don't need to do the right sig figs for 0. 0 is 0. That's all we have. Excellent. Therefore, the net force is 0. Let's try another one here. The figure to the right shows all the forces acting on an object. Use the free body diagram to calculate the net force. We have our FBD. Now notice we have some forces in the x, some forces in the y. Just like when we were doing our vector addition here, we're going to separate those. We're going to focus on x and y as two separate pieces. So I can get the F net x, the net x force. That's going to be, we have 62 to the right, minus 45, because that 45 is to the left. Here I'm simplifying things a bit, which I would recommend doing when you're solving, doing it more in this faster way, where we're implicitly doing our directions just with positive and negative, as opposed to always writing out the directions like we did above. Whatever is more comfortable for you, go with it. Okay, so 62 minus 45, we end up with 17 newtons. And now we can say that this, we said positive was to the east, so 17 newtons east. We can do the same thing for y. Here we have 52 up, 52 down. That means our y force is 0. X is 17, y is 0. That means that our net force, if we add those together as vectors, our net force is going to be 17 newtons east. We can do a therefore there. That's it. That's how we can find our net force. Now obviously we could have a more complicated scenario where we have some net x force and we have some net y force, and we have to add them as vectors, getting the hypotenuse. That's something that can happen. But mostly we'll be looking at this sort of result. Alright, last page here, and now this is a new topic. So we've learned about all our different forces, we've learned about how to do diagrams, we've learned how to get the net force, and now this is separate. We're not going to be talking about this idea a whole lot, but this is what all of our forces are built on. There are 4 fundamental forces in the universe, in everything. As far as we know, there's 4 types of forces, and everything in the universe is made up of those 4 types of forces, which is a big deal. We're still, as physicists, we're trying to find a way to combine these into one force. Gravity is the main problem with that. But anyway, as far as we know, there's 4 types of forces. Gravitational. Well, you know a bit about gravitational force now. So this acts between any 2 objects. And the interesting thing about gravity is that this is only attractive. There's no repulsion, so that means it only pulls, it doesn't push. And that's different from all the other forces. Every other force we have here can push things or it can pull things. Gravity, as far as we know, it can only pull things towards each other. That's our first type of force. Our next force is electromagnetic. Well, electromagnetic, this is caused by electric charges. So if we have two electric charges, they interact some way. They have a force between them. It can attract or repel. So it can push or pull. And you've probably heard something like that before, that like charges repel and opposite charges attract, that sort of thing. That's what we're talking about here. And this is what holds atoms and molecules together. So it's what causes the electrons to stay orbiting the nucleus, and it's what causes multiple atoms to join together into a molecule. Now, in this course, not just in this course, in physics, almost all the forces that we talk about, when I talk about tension, and I talk about friction, and I talk about applied force, almost all of those boil down to electromagnetic forces. So almost all forces that we deal with are electromagnetic. Which is kind of interesting to think about. If I push something, what's happening is, and I'm just going to draw on this paper here, what happens is all the molecules in my hand, let's say this is my hand here, all the little molecules in my hand come up against all the little molecules in the thing I'm pushing. Let's say I'm pushing the wall. And as they get closer, the protons and electrons that are in my hand are repelling the protons and electrons that are in the wall, and they push each other. And that's what's pushing. That's what an applied force is. It's really just electromagnetic. It's the same story with tension and with friction and all of these forces. The only real one we'll be looking at that isn't that way is our gravitational force. And again, gravity is weird. We don't fully understand gravity yet. Okay, we have two more types of forces, strong nuclear and weak nuclear. Strong nuclear, this keeps the protons. Actually, let me just erase that, I'm sorry. This it holds the nucleus together. So if we've got a whole bunch of protons together, you might have thought it's weird that in the nucleus of an atom, we can have a whole bunch of protons, and for some reason they all want to stay together. They're like charges, so shouldn't they want to repel each other? Shouldn't they want to all fly away? Well, they don't, because there's this strong nuclear force that holds the nucleus together. It holds the protons near each other. So it keeps the protons from repelling each other. And it also keeps them from getting too close to each other. They serve a double purpose, because it would be just as bad if a proton and another proton got too close to each other and ended up fusing together. That would be a problem. So the strong nuclear sort of keeps the nucleus all together. And I'll point out that this is by far the strongest of the four forces. And we're going to see that just below here. That's by far the strongest of the four forces, and it's what holds the nucleus together. But you don't see it outside of that nucleus. And finally, we have weak nuclear, and this is what holds a single proton or neutron together. So this is even smaller. If you zoom in on a proton, it's made up of these things called quarks. And the weak nuclear sort of binds the quarks together. So now we're really getting into the serious how the universe works part of physics. And like I said, we're not going to dwell too much on this in this course, but it's important that you've got this foundation to understand what the forces are. Everything we talk about in this course is going to boil down to these four forces. Okay, one last little chart and then we're done. So we've got our four types of forces. We're just going to fill out the approximate strength of them and how far they operate. So if we say that gravity has a strength of 1, we'll just start at that. We'll say gravity has a strength of 1. Then electromagnetic force is much stronger. It has a strength of 10 to the 20. It's 10 to the 20 times as strong as gravity is. Way stronger. Strong nuclear, I said this is the strongest one, 10 to the 38. And weak nuclear, not far behind at 10 to the 25. So notice gravity is way weaker than everything else. Our range, gravity operates on a range basically infinite. You can be on the other side of the universe and we still have some amount of gravitational force from an object. Electromagnetic force, same thing, basically infinite range. Strong nuclear and weak nuclear are on very small ranges and then they disappear. So strong nuclear, even though it's the strongest, things need to be very close together. Less than 10 to the negative 15 meters. And weak nuclear, even smaller. 10 to the negative 18. Last column here, the effect. Gravity can only attract. Whereas all these other ones can attract and repel. And that's it. Those are our forces. I'm sorry this has been such a long lesson, but we really got through quite a lot. At the bottom, there's a bunch of problems. Don't be deceived. They're actually pretty short questions, each one of them. So go ahead and give those a try, and see you in the next lesson.